Okay, thanks to the organizers for the invitation to this really wonderful conference. I've never been to such a conference before, where so many fields and top people in all these fields. It's just amazing. So I'm going to focus on some developments in mainly in large deviations theory in the last few years with applications to random graphs. So let me begin with what is large deviations, since I'm not assuming that people are familiar. So there are two goals of the theory of large deviations. One is to study the probabilities of rare events, and the second is to understand the conditional distributions of random variables given that some rare event has occurred. So for example, what does the world look like if we know that some rare event has taken place? So for example, question A is what's the chance that you will win the lottery, and B is how is your life going to change if you win the lottery? So that's kind of the two main things that large deviations study. And the second question is often more interesting. The first question is just a number. And the second question gives you a more detailed information about the structure. So that's usually more interesting, but then you have to understand the first one before approaching the second. So here's a simple example. If you have never seen large deviations before, so toss a fair coin n times, where n is some large number. And then under normal circumstances, you expect that you get approximately n over 2 heads, and also if you look at number of consecutive heads, you expect about n over 4 consecutive heads. Now, suppose the following rare event occurs. So you get 2n over 3 heads, so many more heads than you expect. So what's the probability of that, first of all, and how do the whole thing change? Given so now there are some tools from large deviations theory. I'll tell you a little bit about how this kind of computation is done. It shows that the probability of this rare event is approximately this. So in this case, it's a very simple example where you can do exact calculations and everything, but there are general purpose tools which apply to many similar problems, much more complicated than this, which allows you to calculate the probability of this kind of rare event. And then you can also ask, if this rare event occurs, then how many pairs of consecutive heads do you get? What's the likely number of? So that's the question. If a rare event occurs, then the whole thing changes. So everything changes. So that's the general thing in probability, that you can make various deductions about a system, but given that some rare event has occurred, all those deductions may be false. So the system as a whole changes completely. So if this rare event has occurred, then it's very likely that you get 4n over 9 pairs of consecutive heads instead of n over 4 consecutive pairs of consecutive heads. So that this is something that you can prove. Okay. So now, how do you do this kind of computation? So I'll just show you a little bit of math here, and then I'll connect it to whatever is going to follow. So how is this estimate obtained? So suppose x1 to xn are independent random variables. Each has probability half of being 0 or 1. And Sn be the sum of these things. So the number of heads in n tosses of fair coin behaves like this random variable. Okay. And then what you do, okay, so this is the most amount of math that I'll show. I'll not go much more than this. So suppose you ask what's the chance that you get at least 2n over 3 heads. So this can be written like this. So choose some parameter theta. This probability is the same as this probability because this event is the same as this event. And then you bound it by Markov's inequality. So the probability that a random variable is bigger than some constant is bounded by the expected value divided by that constant. So that's a very simple inequality. And then you write down e to the theta Sn as a product of e to the theta xi because of the definition of Sn. Then you use independence to express this expectation as a product of expectations. And then these are simple objects which you can compute. So this is something that you can explicitly compute, and then you get this bound. So this is an upper bound on this probability. And then what you do is you optimize theta to get the desired upper bound. And it turns out, and that's a common feature in large deviations theory, that this kind of an optimization gives you an answer which is actually the correct answer. So you can get a lower bound by a different method, but you achieve the right answer. Okay, so this is roughly the sketch of how this kind of an estimate is obtained. Now, the problem is that this example has this linearity which allows you to compute this expectation. So this is the main step somehow, this computation of this expectation, that you can bring the expectation inside the product. So this is what allows you to do this whole calculation, that there's this linearity. Now, and generalizing this, this simple idea, you have this whole area of classical large deviations theory, which gives a set of very powerful tools to deal with linear functionals of independent random variables or random vectors or random functions or more complicated objects. So whole area. Now the thing is, there are no general tools for nonlinear functionals. So this the title of this talk could have been nonlinear large deviations, which I had originally thought about. So this is what I'm going to talk about: nonlinear functionals, large deviations for nonlinear functionals, and how they arise naturally in graphical structures. Okay. So so here's a natural example. Okay, so here is coming to graphs and networks. In the recent time, there has been a huge amount of effort to understand real-world networks. So just in the last talk, Christos was talking about the internet, and there are many examples of real-world networks that people want to understand. Now, rare events, if you consider rare events happening in random graphs and networks, these are often nonlinear in nature. Okay. So for example, consider the following simple model. There are n individuals. Any two are friends with probability p and not friends with probability 1 minus p, or any two nodes are connected with probability p and not with probability 1 minus p, and these form independently. So this is known as the Erdos-Renyi GNP model. Okay? So this is not a realistic model of networks, but it's a first step, and it's a nice mathematical structure. So in graph theory, these are vertices and edges. So these friendships are edges, and these individuals are vertices. Okay, so this is the Erdos-Renyi model on which I will build on. And if you compute the expected number of triangles in an Erdos-Renyi random graph, it's exactly this. It's roughly like n cubed p cubed over 6. Okay? And here's a large deviation question. Suppose you have this random graph, and you ask, what's the probability that there are k triangles where k is some number much bigger than the expected value? So there are many more triangles than you expect. So you can ask it about any graph. Any graph that you observe in the real world, you have some model about that, and then you suppose you observe many triangles. So what's the probability of the rare event? And more interestingly, if this rare event occurs, what is the most likely structure of the graph? So if there are too many triangles, what is the likely structure of the graph? So remember, in the earlier simple example, I asked, if there are many more heads than you expect in a sequence of coin tosses, how many pairs of consecutive heads would you expect given that this rare event has occurred? So you can ask a similar question about graphs, that given that there are too many triangles, many more than you expect, what does the graph look like? Okay, what's the most most likely structure of the graph? So this is an example of a nonlinear large deviation problem, because the number of triangles is the nonlinear function of the adjacency matrix. So the adjacency matrix here is a bunch of independent random variables. So edges are all independent, and the number of triangles is a degree 3 polynomial. Okay, instead of being a linear function, it's a degree 3 polynomial. And when I started thinking about this question, I was surprised that large deviations theory doesn't have the tools to handle this kind of question, even degree 3 polynomials. So linear is okay, quadratic you can sometimes handle, but as soon as you go to degree 3 and higher, there weren't any tools really to handle that, so understand rare events. And we'll see why. There are non-trivial things happening. Okay. So so what do you do? So for this particular problem, this was developed in a paper that I wrote with Raghu Varadan. And this used Samaridy's regularity lemma and theory of graph limits developed by Laszlo Lovász and co-authors, a long list of eminent people, including two who are present in the audience here, Jennifer and Christian. It's a big development, lots of very important papers, and luckily we now have a book. Lovász has a book which includes this development, this theory of graph limits. So what do you mean by the limit of a sequence of graphs? So this abstract setup that has been developed. And we use that, and we use this tool of Samaridy's regularity lemma. And this helped us build this this theory of large deviations for random graphs. So here is an example. So let me give you an application of this theory to show what kind of things we can say. So recall this Erdos-Renyi random graph model, which is n vertices, any two are connected with probability p by an edge and not connected with probability 1 minus p. The edges are all independent. And let t be the number of triangles. Let ET be the expected number of triangles. Okay. And then you ask, what is the most likely structure of the graph if the rare event, this rare event occurs, which is the number of triangles is at least 1 plus delta times the number of expected number, where delta is some positive constant. So let's say number of triangles is 2 times the expected number of triangles. Okay. Or 1.5 times the expected number of triangles. So what does the graph look like given that this rare event has happened? So there are many ways that this can happen, right? All the extra triangles may be contained in some small set of vertices which are highly connected among themselves. Or it may be that there is just an excess number of edges spread out uniformly all around the graph. So there are many different ways that this can happen, this extra number of triangles. So what is the most likely way that this is going to happen if this rare event occurs? So the large deviations theory implies that both scenarios can happen. In fact, here's one of the most surprising results that came out of this. So it says that there are two numbers, delta 1 and delta 2, strictly positive, so that if this delta is between 0 and delta 1 or bigger than delta 2, then conditional on event E, the graph just behaves like the Erdos-Renyi graph for some larger parameter. So it's just like a lot of extra edges are present, uniformly distributed extra edges. That's why there are these extra triangles. However, between these two numbers, the structure is not an Erdos-Renyi graph. So we don't know what it is, but we can show that it's not like an Erdos-Renyi graph. There is a heterogeneity. The edges are not, the extra triangles are not coming due to a uniform structure. So there is some, condensation somewhere. There is some accumulation of edges somewhere, and we don't exactly know what this structure is. We still don't know. So this existence was proved in this paper. Existence of these two numbers, and then actual formulas. So this is actually complicated, so I cannot show these formulas. So it's not so easy to state. These formulas are derived later by Lubetzky and Zhao. So this is, this is kind of a surprising thing, even from the statistical mechanics point of view, that usually you expect that if you don't deviate too much from uniformity, you get roughly this high temperature phase in statistical physics, where you get close to uniformity, and then then there is a symmetry breaking, and then you get a phase. Here it's different. Here there are two things. So if you're close enough to the original model, then you get just uniform spread of edges. Then the symmetry breaks, but then the symmetry comes back. Okay. So here is to summarize. If the number of triangles exceeds the expected value by a little bit or by a lot, then the most likely scenario is that there is an excess number of edges spread uniformly. On the other hand, there is a middle range in which there is a clustering of edges in some small region. So this we still don't understand what it is, but it can be rigorously shown that it is not like an Erdos-Renyi graph. And when I say it is like an Erdos-Renyi graph, it is not like an Erdos-Renyi graph, this is all can be made precise in the language of graph limits that I mentioned a little while ago. So there is a mathematical language now in which you can express this. Okay. So here is one nice thing that the nice thing about math. These results could not have been guessed. So there are these formulas from which these are derived. So a priori we didn't know that, and it's always pleasant when something like that happens. So this has been extended, and there are more realistic models of random graphs. So there is this exponential random graph models where these are used in social networks. So it has been extended to that. Now there is a problem with this whole setup, which I'm going to say now. It applies only to dense graphs. So this whole theory of graph limits that we are using and Samarida's regularity lemma, it's all for dense graphs. Okay. So what is a dense graph? So graph is called dense if most vertices are connected to a sizable fraction of other vertices. Okay. So for example, if you have an Erdos-Renyi graph with 10,000 nodes, so there are 10,000 people, and any two are friends with probability 0.3, then each person is connected to roughly 3,000 other vertices, and that's a dense graph. Okay, because every vertex is connected to a sizable fraction of the other vertices. Now, in real networks, this is not true. Okay, real networks are usually sparse, so every node is connected to a small fraction of the remaining nodes. And the graph theoretic tools that we use for this whole analysis are useful only in the dense setting. So that's a big problem. And the central reason somehow is that the Samarida's regularity lemma for sparse graphs, there is no adequate version of that we can use for this large deviation problem. I mean, there are versions for slightly sparse graphs, but really sparse graphs, you don't have that. So the main issue is the following. So when you want to enumerate the number of graphs with a given set of properties, so this is what you really want to understand. So how many graphs are there with m edges and k triangles? So this is the kind of thing that you want to understand. Now, what Samarida's regularity lemma does is it gives a way of approximately doing these countings. Okay? So what the regularity lemma does is that it classifies a set of dense graphs on n vertices into a number of types. So very roughly speaking, number of types, and the number of types depends on the how much accuracy you want. So when I say when I say approximate counting, the degree of approximation determines this number of types that you get. Okay, and it doesn't depend on n. Now, in the sparse setting, we do not know how to do this kind of classification. So ideally, you would want a classification where in each class, you would be able to tell, how many triangles does it have, how many other, subgraph counts, and so on. In the sparse setting, we do not have this kind of classification. So in what graph theorists would call a counting lemma, we don't have that. And in the sparse setting, many things may happen. This excess number of triangles can occur because there are extra edges distributed uniformly, or a small number of vertices that are highly interconnected, or a small number of vertices that are highly connected to the rest of vertices, and many other things that you can think about. So this is the last development that I would like to talk about. So there's this nonlinear large deviations, which bypasses this regularity lemma to a certain extent, and it gives you a different way of approaching this thing. And there is a concrete outcome of that. So this theory, soon after this was developed, Lubetzky and Zhao, they could solve certain things that weren't solved here, and they showed this. Okay, so this is one formula that I would like to show here. So if you consider the GNP random graph, the Erdos-Renyi random graph with n vertices, probability of connectivity P, and T is the number of triangles, and P is going to 0. So ideally would like P going to 0 like n to the minus some small power, n to the minus half or something. But here it's, we cannot get better than this right now. So n to the minus 1 over 42. So slowly going to 0. Then the chance that the number of triangles exceeds the number of edges by a factor of 1 plus delta is roughly e to the minus n squared p squared log 1 over p times a constant depending on delta, where the constant is the minimum of delta to 2/3 over 2 and delta over 3. Okay. So this question has a long history. So understanding this probability, people in combinatorics and random graphs have been thinking about for 30 years, and for a long time, even the right dependence on n and p was not known. And then there's a long list of developments. Eventually, we understand now that this is n squared p squared log 1 over p. But the dependence on delta was completely open. And this was finally solved here using this nonlinear large deviations theory, that this is this number that you have. Okay. So it's a lot of hard work, and so as I said, this is a very old unsolved problem, and I say it's an almost complete solution because we still cannot go like p going to 0 n to the minus arbitrary powers. So we get stuck at this slow rate, n to the minus 1 over 42. That's what we can get. And this has been generalized in this later paper to not only to triangles but to other structures. And so this is a nice simple formula, but if you consider to other structures, you get more and more complicated formulas. For instance, if you instead of triangle you consider 4-cycle, you get something like square root of 1 plus square root of 1 plus delta, something like that. So solutions of equations. No. So my work with Wadia is only for dense graphs. So this is p going to 0. P going to 0. So for p fixed, we have a formula. But that formula, we cannot, we don't know how to solve that. So there is a formula, but there is no explicit solution. Okay. So here is the list of future directions. So the main problem is that we do not yet understand the nature of sparse graphs. So we understand some sparse graph structures, but not all possible structures. And the thing that can really solve it is getting a suitable version of Semerides regularity lemma for sparse graphs, which doesn't exist at this point. And some progress has been made using this large deviations theory, but one needs a better version of this theory. And in the real world, these networks that appear in the real world and the networks that are theoretically analyzed, there is this gap. And if you want to know more details, I tried to finish something quickly. So there's this monograph, and also it contains a whole bunch of results from this graph limit theory. So it's a self-contained presentation that I have there. Okay. So thank you. That's all.
You said it was like 2010. For the last 5+ years, we have developed 2 different sparse graph theories, which only overlap in dense graphs. And they both have Semerides lemmas. So we do have, in both of them, Semerides lemmas for sparse graphs, which was actually the kind of breakthrough that was necessary to get sparse graph limits. One of them has already been published, or at least the paper's been around for a few years with Yufei Zhao. And another we're doing with young Latsi Lovas, with Latsi Lovas Sr., and that one we're just finishing the paper. But the first one has no counting lemma. The second one does have a counting lemma in addition to a Semerides lemma, and I believe you will be able to do all of all of this to actually get an analog of your work with Raghu Varadhan using some of that new stuff.
I see. So I didn't know about the second work. So the first one I knew.
Right. Well, I mean, the preprint isn't out yet, even though the work has been done for about a year, but or 6 months or something.
Oh, that would be fantastic.
So because it turns out to be the one that that we think the combinatorialists are going to love because it does have an analog.
Yeah, that would be fantastic. That would be great.
Great. Yes.
Yeah. So quick question was. Yeah, sort of here.
Where? Oh.
So, is there anything surprising in the other direction? Too few triangles, if you see in a graph?
Yeah, so that has been worked out. So, so too few graphs is not fully understood. So, if you too few triangles, if you go down a little bit, you still get to see Erdos-Renyi. But as you go down more and more, you start getting bipartite kind of structures. And so you don't get this double phase transition. So it doesn't go back to Erdos-Renyi. So if you have closer and closer to zero triangles, then you get more and more like a bipartite structure.
Yeah, yes, absolutely.
I wonder, over here. Yeah.
Oh.
I wonder if you make a single observation on a graph and then you see this kind of pathological behavior that you were talking about where you see this clustering and what have you. Can you go back and say, oh, I must be in this range of, can you say something about going backwards, you make an observation, can you say something about the delta 1 and the delta 2? I'm in this middle of delta 1 and delta 2 and say something about what can you know that you've made can you know that you've made a rare observation on a graph just from one observation?
So that would be a statistical question. So there are many things that you can estimate about graphs using just one observation of the graph. And so I didn't think about this particular question, but there are analogous questions like in this exponential random graph models, which are very similar. You can estimate parameters. So there is some work on estimating parameters in the exponential random graph model. That if you observe just one graph and then you can estimate parameters from the graph, and then there are so it should be possible. That the thing about this setup is that in this middle range. We know very little about the structure of the most likely structure of the graph, except that it's not Erdos-Renyi. So we can prove it's not Erdos-Renyi, but we don't know what the structure is. So we don't understand that. Yes.
Go there and then Christian. Yes, you first. Yes.
Yeah. Theory, you would need a topology which where the number of triangles and so on are continuous, but
at the same time not too strong.
Not too strong. So that's that is of course there. But more generally, if you consider, let's say, 3-term arithmetic progressions, things like that. Mm-hmm. So the hindrance more is in this nonlinearity, that you cannot do this calculations about these functions, and so that's one place where it comes in. And so in a different setting, maybe you would need to figure out a different topology, and you need to work with that. But the main thing about Samardiz's lemma is that it gives this compactness of the topology, and that compactness is the key key thing.
Okay, Christian.
So I have a question coming sort of from my original physics background. In physics, we often talk about equivalence of ensemble. So we have things like, I'm sitting here. So we have something like, we know that you could either fix the energy of a system or you could fix the temperature, and then I can adjust the temperature in such a way that in average, the average energy is whatever I want. Yeah. And the fact that you can always do that by a Legendre transformation in the end is sort of known as equivalent of ensembles. Yeah. And for these exponential random graphs, this is sort of a little iffy, right? We in general don't know that. So can you comment a little bit how that enters
exactly.
Here?
So the first instinct of a statistical physicist for this problem would be to build a model where you have e to the beta times the number of triangles and so on. Now, but that will not work because you see a jump. So as you increase your parameters, the number of triangles will increase. Okay, so you have an equivalence of ensembles, but then you have a jump. Okay, then you have a first order phase transition. So there's a whole range of intermediate range of number of triangles which is not captured by this statistical physics model. So you cannot cannot really use that to understand. So that's why. So initially, I was trying with this statistical physics kind of approach, but then it became apparent that that will not work because the exponential random graph kind of models will not capture this intermediate range.
But even the intermediate range has some history in physics, right? You get to wolf shapes and things like that, how you actually go between, right? In the Ising model, you would have naively the same thing. You can sort of go above the sort of spontaneous magnetization or below minus the spontaneous magnetization, and you would have a jump between minus spontaneous magnetization and plus, and then we can sort of look at wolf shapes and things like that. So things like that don't happen here?
It may, but that's the kind of thing that we don't understand here. So, so the analog here is more like in the Ising model, not varying the external magnetization. Suppose you vary the temperature. As you vary the temperature, the magnetization goes from 0, but then starts off continuously. But here, the number of triangles will increase as you vary the parameter beta. But then it will jump to something else and it will go like this. So.
Okay, perhaps one brief question and then we close.
So, is there some hidden symmetry in this delta 1, delta 2 which exchanges the two so that there is really one phase transition in a modified system, or are these really two different?
So this delta 1, delta 2, I'll tell you what the formulas are. So there is this function, this nonlinear function which one can construct using the entropy. It's the entropy function applied to composed with the cube root function or square root function, something like this. So this function looks like this, and then you build the convex minorant, and there is an intermediate region where the convex minorant is not touching the function. The function is different, and those 2 points are delta 1 and delta 2, and that's where, So that's.
Nati, very brief.
See anything special as you approach either delta 1 or delta 2 from either sides? So that you're not yet at the transition, you're a little before. Do you know that anything is going to happen soon? Is there any symptom of it?
So the thing is, it's hard to get that kind of refined answer using the machinery that is used here, Samaridy's lemma, because Samaridy's lemma is highly non-quantitative. I mean, it gives this tower type bounds. So you need much more delicate bounds. Now, there is numerical work which shows that all of these formulas and so on that you get, they're very good approximations even for small n. But if you want to get numerical control, quantitative control, this theory is not going to give you that. It will require some other tool which we don't know. We don't know yet, and so this is kind of too crude to answer this kind of refined question. But